In this video, we're going to talk about section 4.1, vectors in Rn. What we mean by that is vectors that have real number components. It doesn't matter how many of them they are. And they look like they're n-tuples, like ordered pairs, ordered triplets. They look like that, but they're really n components. And so this is one space, two space, three space, so on. And they would make these nice vectors for us that we're going to be able to draw. Everything that we're going to be dealing with here that we're going to draw is 2D. You can draw in 3D, but we do that more in Math 265 than we do here, and you'll deal with some vectors in there that are R3 vectors, but we'll deal with R2 vector, R1 and R2 vectors here for right now with drawing. So let's start with problem number 3, and it's the vector u is equal to, and in this class we'll use the parentheses to denote a vector. In Math 265, we would write it this way with these brackets that look like this, just so that they don't get mixed up with ordered pairs. We don't talk about ordered pairs in this class. Really, everything is matrices and vectors, so there's no confusion with using the parentheses. But if you're in a situation where you're talking about points and vectors, then you would probably want to use those angle brackets there to denote your vector. All right, so let's go ahead and let's draw this directed line segment here. Try and keep things lined up on the grid. That's why I have the graph paper here. So we want to go 2 to the right and 4 down from the origin is right there. We'll just draw a directed line segment there to represent the vector u. Number 5 says u is equal to -3, -4. So we'll make a coordinate plane here. We're going to go 3 to the left and 4 down and right here. Wish I had my, oh, I do have my straight edge here. Where is that at? Right here. This is kind of, I'm going to zoom in a bit, turn this around. About to say I wish I had a straight edge, but the application does have a straight edge in there. I don't think that it's going to work with all the problems, but there we go. So something like that. And I can get rid of it here off to the side and just let me click to get rid of it because I don't need it for right now. So that was 3 and 5. Let's look at number 7. And it says that vector u is equal to 1, 3. Vector v is equal to 2, -2. And I want to find u plus v, and I want to show it geometrically, as well as doing the arithmetic here. So there's my arithmetic. Let's see if I can show that with geometry as well. So we've got x-axis and y-axis, And we're going to start with vector u is 1, 3, right there. I'll draw that. That's u. And then from that endpoint there, I want to go 2 to the right, 1, 2 to the right, and 2 down is going to take me to there. So that's vector v. The vectors don't have to start at the origin. They can start anywhere in space and they're the same vector. So I put them head to tail here. And then the resultant here, u plus v, is going to go 1, 2, 3 to the right and 1 up. So that's u plus v. And that's how I do addition of vectors with my head to tail method, or you can do your parallelogram method if you want to stick the two vectors such that they make a parallelogram here. Then this diagonal right here is going to be the side right here. It will be your resultant. So anyways, that is number 7. We're going to move on now to number 13. Is if v is equal to u plus 2w and u is equal to a negative 2, 3, and w is equal to negative 3, negative 2. We want to first do the math here to figure out what v is. So I'm going to do this multiplication first because I need to know this vector for my geometry that I'm going to be doing here in a minute. So that's negative 6, negative 4. And then this is negative 2 minus 6. And 3 minus 4 gives me negative 8, negative 1. So let's do my best here to give myself enough x-axis to the left. I'm going to move my y-axis over here to give myself enough room over there. And I want u is negative 2, 3. So there's my vector u, and w is 2w is negative 6, negative 4. So from here, 1, 2, 3, 4, 5, 6 to the left, and 1, 2, 3, 1, 2, 3, 4 down puts me here. So that is there. I can kind of sort of connect that to the origin. Then there's my 2w, and we have u plus 2w here. And this point over here is negative 8, negative 1. So that is my directed line segment. My vector will be negative 8, negative 1. Next problem we're looking at will be number 17. Number 17 says that v is equal to 2, 1. And part A asks us to find 2v, which is 2 times 2, 1, which is 4, 2. And we're supposed to draw that. So that's going to be, it's really hard to do this freehand. I do this with graph paper and straight edge most of the time. So 1, 2, 3, 4, 1, 2. It's out here. There we go. 4, 2, that's 2v. All right, now the next one asks me to find negative 3v. So that's negative 3 times 2, 1 is a negative 6, negative 3. So to graph that, have negative 1, 2, 3, 4, 5, 6, negative 1, 2, 3. So we're out here, like so. Negative 3v, so negative 6, negative 3. And then c is 1/2 v, is 1/2 of 2, 1, is 1, 1/2. So 1 to the right and 1/2 up is right there. So that's 1/2 v. And that's it for number 17. We'll move on to number 23. 23 gives us a vector u that's 1, 2, 3, a vector v that is 2, 2, negative 1, and a vector w that is 4, 0, negative 4. And it tells us to find vector z where 3u minus 4z is equal to w. So we're going to rearrange that and make that negative 4z is equal to negative 3u plus w, and z is going to be equal to 3/4 u minus 1/4 w when we multiply everything by negative 1/4 left and right there. So z is equal to 3/4 of u minus 1/4 of w. So that's going to be 3/4, 3/2, 9/4 plus negative 1, 0, 1. And so that's 3/4 minus 1, 3/2 plus 0, and 9/4 plus 1 is 3/4 minus 4/4. 3/2, 9/4 plus 4/4 is negative 1/4. 3/2, 13/4. Number 29 is the next problem. And we have vector u is equal to 4, 0, negative 3, 5, and vector v is equal to 0, 2, 5, 4. And we're asked to find u minus v, which is equal to 4, 0, negative 3, 5, minus 0, 2, 5, 4. That's 4 minus 0, 4 minus 0, 0 minus 2, negative 3 minus 5, 5 minus 4. So that's 4, negative 2, negative 8, and 1. Part B says that we want to find 2 times vector u plus 3 times vector v. And that's going to be equal to 2u plus 6v. So that's equal to 2 times 4, 0, negative 3, 5, plus 6 times 0, 2, 5, 4. So that's 8, 0, negative 6, 10, plus 0, 12, 30, and 24. That's 8 plus 0, 0 plus 12, negative 6 plus 30, and 10 plus 24. That's 8, 12, 24, and 34. Part C asks us to find 2v minus u. Watch out that v is before u here. That's 2, 0, 2, 5, 4, minus 4, 0, negative 3, 5 is 0, 4, 10, 8, plus a negative 4, 0, 3, negative 5. 0 minus 4 is negative 4. 4 plus 0 is 4. 10 plus 3 is 13. 8 plus negative 5 is positive 3. Negative 4, 4, 13, 3. Let's go ahead and look at number 35 next. And that's u is equal to 1, negative 1, 0, 1, and v is equal to 0, 2, 3, negative 1. We're told to solve for w, where 3w is equal to u minus 2v. So that means that w is equal to 1/3 u minus 2/3 v. W is 1/3 of 1, negative 1, 0, 1, minus 2/3 of 0, 2, 3, and negative 1. So w will be equal to 1/3, negative 1/3, 0, 1/3, plus a 0, negative 4/3, negative 2, positive 2/3. So w is 1/3 plus 0, negative 1/3, minus 4/3, 0, minus 2, and 1/3 plus 2/3. That makes w equal to 1/3, negative 5/3, negative 2, 1. Let's now look at number 41, which starts our section of asking us about linear combinations. We're going to use what we know about matrices for this. Even though this one doesn't really need to be solved with a matrix, we could just use a system of equations. U is equal to 1, 2, and W is equal to 1, negative 1. And we want to know if we can get some constant multiples of u and w, that I'm going to say a u plus b w is equal to v, which is equal to 2, 1. I'm going to set up a matrix here where u goes down this way, v goes down this way. I'm sorry, w goes down that way. So this is my u's and my w's that make up v, hopefully, like that. And then you can reduce row echelon form this, and you get 1, 0, 0, 1, and you get that a is going to be equal to 1, and b is going to be equal to 1. And so you get u plus w is equal to v. Let's go on and look at number 43. U is equal to 1, 2. W is equal to 1, -1. And then V that we're interested in is equal to 3, 3. So we want 1, 2, 1, -1, 3, 3. RREF that. 0, 0, 1. And this is 2 and 1. So 2u plus 1w is equal to v. Let's move on to number 47. And v is equal to 10, 1, 4. u1 is equal to 2, 3, 5. u2 is equal to 1, 2, 4. u3 is equal to -2, 2, 3. 47 here. So we want to set up our matrix here. This is 2, 3, 5, 1, 2, 4, -2, 2, 3, and we want that to make up 10, 1, and 4. We want vector v to be made up of these 3 components here, and we will RREF that, and we will get our solution to be 1, 2, and -3. So that's u1 plus 2u2 minus 3u3 is equal to v. Last but not least, let's look at number 49, which is v is equal to 0, 5, 3, 0. u1 is equal to 2, 3, 1, 1, 2, 2. u2 is equal to 2, 3, 5, 6, and U3 is -3, 1, -4, 2. So we have 1, 1, 2, 2, 2, 3, 5, 6, -3, 1, -4, 2, 0, 5, 3, 0. This already looks off to me because I should have as many U's as I have dimensions. When I had 3 dimensions here, 1, 2, 3, I had 1, 2, 3, but I have 1, 2, 3, 4, and only 1, 2, 3 vectors to make it up. That should create a problem, and it does. So when we try to RREF this, then we get 0, 0, 0, 1, like that. And this last one is completely false. It's impossible, is what that's saying, to do that. So it is impossible to write V as a linear combination of vectors U1, U2, and U3. All right, that's it for this video, and we will come back next time to talk about section 4.2, which is vector spaces. That's going to be quite a big topic there. So I'll see you for the next video.